I want to welcome you to another theory of statistics class. Of course, before I get started today, I have uploaded exam one practice without solution in accordance with what I said last week. So today, I'm actually going to release a solution to exam one practice. Of course, my TA is going to walk you through the practice in the lab. I'm going to say this. Those are the areas the exam one we covered. So I needed to spend more time on those areas. I'm not going to go outside the areas. Does that make sense? Okay. Let me say this. The topic that we started last week will not be part of exam one. Like the one we're doing currently will not be part of exam one. So, okay, you can hear me, right? All hear me? Okay, so we I want us to actually start from where we left off the other time. We we started some probability distribution of continuous type. I introduced you to normal distribution, and of course, we actually are going to pick up from there. Now, I was talking about normal approximation to the binomial. We got situation whereby, um, we can approximate binomial distribution with normal in a situation where we have a large numbers of trials. It's, Demover since 1733 was actually trying to solve a binomial problem. And because the numbers of trials is very large, using binomial formula was very complex thing, to achieve. And because of that, he approximated, given certain conditions, he approximated, that with the normal distribution. And of course, that's exactly what I'm trying to say the other time. Give me 1 second. Now, if you take a look at this, if Sn, okay, Sn is a binomial variable, okay, with a parameter n and p. Of course, we all know, okay, the two parameters in binomial are n and p. N is the numbers of trials, p is the probability of success. Okay, situation where the numbers of trials is large. That's why you see here, n tends to infinity, means I have large numbers of trials. And, if I have large numbers of trials, of course, we can have situation whereby that can be represented by a normal curve. Okay, that was what the mover did. Now, take a look at this now. So which means I can actually use a normal curve to figure out, probability if we're dealing with the binomial. And that was why I said under the theorem, when S follow binomial with parameter n and p, of course, we can use the idea of a z-score. And the idea of a z-score is because if I'm talking about normality, okay, if I'm talking about normality, then normality facilitates standardization. So if I've achieved normality, because I achieve normality when the numbers of trial is large, okay, binomial tends to become a normal. And when binomial becomes a normal, the normality will facilitate what I call standardization. And when I say standardization, it means we can use a z-score. Using a z-score is going to make the whole computation easy because we can actually make use of a table instead of going by the way of rigorous calculus. That's exactly what I mean. But what was the condition? The condition imposed is this. NP has to be greater than 5. N into 1 minus P also has to be greater than 5. The NP in that situation means the expected number of success. And N into 1 minus P means the expected numbers of failures. We all know binomial distribution model outcome, that are dichotomous. Dichotomous means it's either we record success or failure. Now, I think I was showing you this proof the other time. Mathematically speaking, this is how, they were able to prove that we can actually go from binomial to, a normal distribution using a Stirling formula. I think I showed you this last week. We started from the binomial here, okay, and using the fact that the n factorial equal to that. Wherever you see n factorial now, you see that? Because I'm using this. So n factorial can be written as that. K factorial can be written as that. N minus k factorial can be written as that. So now we go all the way to simplify, and at the end of the day, we're using what I call, the Taylor series, and at the end of the day, we are able to arrive at, a normal curve, okay? We're able to arrive at a normal curve. Now, but there's something I want to tell you. Binomial distribution is discrete, while normal is continuous, okay? Binomial, of course, we all know, binomial distribution is, for discrete random variable, normal is for continuous. Okay? Now, for us to be able to approximate a discrete, we want to approximate a discrete with continuous, that is going to come with error. Whatever approximation we do in life will come with an error. Okay? Now, if we now want to try and we need to make some adjustments, okay, whenever this approximation is made. And their adjustment is what we call continuity correction. So the idea of continuity correction is actually needed because of the fact that, whenever we are making, we're trying to make approximation, there's going to be an error that comes with that. Of course, I want to use a continuous distribution to approximate a discrete. Of course, that's going to come with error. And if I want to minimize the error, due to this approximation, I'm actually going to use continuity correction, and I need you to pay attention. In binomial, if I want to solve a problem, okay, probability of S equal to n. For instance, probability of S, take an exact value. I want to use binomial, but because the numbers of trial is large, and I want to use, normal, and normal is continuous, and don't forget, every continuous distribution will normally seek redress in an interval. Because of that, if I want to use normal, this is what I'm going to do. I'm going to subtract 0.5, okay, from that particular variable, then I'm going to add 0.5. Then if I want to find normal, I'm going to find the probability of that random variable lies in the lower bound and the upper bound. What if I'm dealing with the greater than n? If I'm dealing with greater than n, I'm actually going to consider this. I'm going to add 0.5 and still pursue the probability of S greater. If I want to do less or equal to n, okay, that's what I'm going to do. Less than n, that's what I'm going to do. Greater or equal to n, that's what I'm going to do. If we don't do this, the approximation will have a huge error. I'm going to say that again. If you don't do this, the approximation will come with the error. Okay, an error is not good. So how do we minimize that? And that is the reason why we have this continuity correction in place. So the idea behind continuity correction is to minimize the error due to approximation. Okay, now if I have this, how am I going to implement that, please pay attention. Pay attention, okay? If I have already settled for this is what I want to do, okay? If I want to do, for instance, if I want to find the probability of a random variable inclusively lie between A and B, and I want to use the idea of a normal approximation, this is what I'm actually going to do. I'm subtracting 0.5, and I'm adding 0.5. Then I'm going to find the probability of a z lying between that. Of course, my end, you know, from the binomial problem, you're actually going to be given what is the numbers of trials. You're going to be given P, the probability of success as well. Now, I need you to pay attention to all of this, okay? If you pay attention, of course, you remember the other time I said when we are working with continuous, right? All of this is supposed to be the same. Please pay attention. When we're working with continuous, everything here supposed to be the same. All of this supposed to be the same if we are working with continuous. But right now, we are not working with continuous. We are going from binomial to normal, okay? And each of that will give a different result because we're doing approximation here. Is that what sense? Okay, so please take note of that. Now, I'm actually moving. I'm actually going to move. Now, let's have an example. Are you ready? You want to have an example now. The reason why you need to take this area very serious, of course, this is like a countdown to midterm 2 because the way I'm actually going to have the exam, okay, the areas, the midterm 2 is not going to be cumulative. Okay, where we left off in midterm 1, the topic we left off, like this is like where we are now, the continuous probability distribution, that is where the midterm 2 will start. Does that make sense? Okay, and that's why I want you to pay attention. The moment you don't understand, please make sure you ask me question. Okay, now let's have an example. Suppose a fair coin is tossed 100 times. Okay, what is the probability that will be more than 68? Please pay attention. What I'm seeing here, okay, this is obviously a binomial question. Why is it a binomial question? Can somebody tell me, why is this a binomial problem? Go ahead.
Coin toss has 2 options.
Exactly. Send me a message for extra credit. Because when you toss a coin, you have 2 possible outcomes, head or tail, and that's a binomial process. And the fact that, somebody, we can also call that a Bernoulli process, okay? But can somebody tell me again what distinguishes between Bernoulli and binomial here? Go ahead.
There are only 100 trials.
Exactly. Why Bernoulli is for just 1 trial. Good job. Now, because I have n equal to 100, right? The numbers of trials is more than 1, and I got 2 possible outcomes. Then what I'm actually going to do here, I'm actually going to use binomial. But you know what? Using binomial for a problem like this, because the numbers of trials, why is it that there's going to be an issue? I'm actually going to let you see. Because on a nomogram, if you take a look at what I have, of course, my n equal to 100, okay, and my p, okay, my p will be equal to half because I'm working with a coin, right? That's what I'm working with. Now here, my x is the numbers of x because that's what they're interested in. They said, what is the probability there will be more than 68? Okay, x, that is the number of x. Now you want to find, okay, the probability of the numbers of x greater than 60. Number of x greater than 60. That is what you want to find. And of course, go ahead.
So instead of using the random variable x, what's the reason why we're using s suffix n?
That's a very good question. Because I can decide to use anything as random variable, provided I just define. Like right now, you know what I want to do? I want to use X, and I'm telling the world my X represents that. So if I'm also using this, all what I just need to do is to tell the world what it represents. So I'm using X right now because, students, they're familiar with X, 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 but any other alphabet can also be used. Does that make sense? Okay, now, the binomial formula is this. Okay, the binomial formula is this. If I want to rewrite this guy now, okay, I can write that as n factorial, x factorial, n minus x factorial, p raised to power x, 1 minus p raised to power n minus x. Okay, if you take a look at what I have now. Now, if I want to do s greater than 60, okay, and don't forget, in the binomial formula, s starts from 0, 1, 2, 3, up to n. Okay, now, x greater than 60, okay, I'm actually going to have 100, that will be 100 combination, So I'm going to continue, from 60, 61, 62, I'm going to go all the way. That's going to waste my time. And the fact that the sample size is large, okay, that's going to be an issue. Okay, so what we can do, we can actually use the idea of approximation, the normal approximation. If I want to use normal approximation, what I need to do, number one thing I need to do, I've identified my n and p, right? Then I need to find what is the NP. Okay, I'm just going to multiply 100 by half. That will give me 50. Then I'm also going to get the standard deviation. Okay, because I want to use the idea of a z-score. If I want to use the idea of a z-score, why am I using z-score? Because I'm using, initially, I've investigated, maybe I investigated and I realized that, NP is 50. And under the condition is that NP has to be greater than 5. Do you see that? NP, the condition is that NP has to be greater than 5. And that guy also, n to 1 minus p, also have to be greater than 5. The moment that hold, I can use normal approximation. And if I can use normal approximation, then I can use standardization. Because normality facilitates standardization. And then when I mean standardization, I can make use of the z-score. Okay, now if that is going to happen, right, I'm going to move right now. I've gotten that. Now, if you take it, and I want to find the probability of s greater than that, okay, s greater than 60, okay, say there will be more than 60, then if I want, now if you take a look at what I'm doing here, I'm already applying the use of z-score, where I'm going to have the Sn minus the mean divided by the standard deviation. Now, the standard deviation is 5, if you see. Then, instead of me to be looking for the probability of Sn greater or equal to 60, I'm going to be looking for the probability of a z greater or equal to 2. All what I just need to do is to go to the table and check. Okay, now greater or equal to 2, don't forget, that will be 1 minus the probability of z less than 2. What you can check from the binomial table is less than 2. Okay, now with the result that we have right now, okay, that has saved us from the rigorous situation using the binomial formula directly. We've been able to use, the idea of a normal curve. Okay, and that's, we have an easy probabilistic computation in the process. Now, I'm going to give you more example. But right now here, I have not applied a continuity correction. Okay? So I'm going to tell you when the continuity correction will be applied. Now, take a look at this. This is another question. Suppose a die is rolled 180 times. What is the probability that a 3 will be showing more than 50? Now here, we're talking about a die. Okay? The sample space is 1, 2, 3, 4, 5, 6. And the probability of whatever event will be 1 over 6. Okay, that's 1 over 6. And of course, if that is 1 over 6, if you want to get, you can get your NP, which should be the number 180 multiplied by 1 over 6. That's going to give you 30. And the moment you have 30, of course, the condition under which binomial can be approximated with normal has already been met, because we expect NP to be greater than 5, and this is greater than 5. Okay? Now, you find the standard deviation, and what you're gonna do next is, okay, if I want to find the probability of that particular random variable now, okay, if I want to find the probability of the particular random variable equal to that, or what I'm going to do, so if I want to find the probability of that now, is equivalent to finding the probability of a z greater than 4. Let me tell you this, the moment you end up in finding probability of a z-score, okay, of course, that would be easy. When you're working with a z-score, that would be easy. That is just the idea, okay? But we got a condition that needs to be met, okay? I'm going to move right now. Now, take a look at this. Suppose a drug is supposed to be 75% effective. It is tested on 100 people. What is the probability that more than 70 people will be hurt? This is a binomial question, okay? Because the mention effective is either the drug is effective or not. That is binomial. And another reason why we're confirming binomial is because of the fact that the numbers of people they want to use is more than 1. They want to use 100 people. Now, the question here is like, what is the probability that more than 70 people will actually be hurt? Okay? Now, what we need to do again, we need to identify what are our parameters. Okay, n and p. We know n equal to 100 here and p equal to 0.75. The 0.75 is coming from the 75%. Okay? Now, the next thing I'm actually going to do, I'm going to do my investigation again, multiplying 100 by 0.75. If I multiply 100 by 0.75, that will give me 75. That is greater than 5. Okay? The condition required for, binomial to be approximated with normal, that's already satisfied. Okay? Now, then I need to get my standard deviation, which is going to be square root of n into p into 1 minus p. Now, after getting that, I should be ready, to use a z-score. Using a z-score, at the end of the day, we're actually going to have a very easy probabilistic computation. We want a situation whereby if there's a problem and it requires mathematical strategy, we don't want to use an approach that is going to be complicated. And that's why we're looking for a way to simplify things out. And that's why if a condition is met, of course, we can use the idea of a normal. And that is why in the statistical world, we normally want situation whereby the distribution of our data will be normal. Because if the distribution of data set is normal, normality facilitates standardization. Standardization will facilitate the use of z-score. The moment we're using z-score, we can check from table. That will enable us to ignore rigorous calculus. Okay, now, you know what I want to do right now? I want us to start from binomial. And, when we have a problem, we want to solve it binomial way. We also want to solve it using normal approximation to binomial. Not only that, we can also use Poisson distribution to approximate binomial. Let me tell you this. We got conditions under which normal can approximate binomial. Poisson can also approximate binomial. But let me tell you this. If you don't go through approximation, if we're able to solve the problem using binomial, okay, of course, the answer that we're going to get is not going to be subject to error. Binomial, if I use binomial approach for binomial problem, that will give me the exact result I'm looking for. But why do you think I want to consider approximation? Maybe it's become complicated using the binomial. That's why we want to go for approximation. And when you go for approximation, you expect to have an error. But you know what I want to do? I want to show you right now. And I need everyone to, to be focused. I want you to take a look at this problem. We're going to solve it binomially. We're going to solve it using normal approximation to binomial. We're also going to solve it using Poisson approximation to binomial. And we're going to compare results. Is everybody ready for that? Now let's get started. Now here, suppose that we roll 2 dice 180 times. 2 dice 180 times. Let E be the event that we roll 2 5 more than once. Okay, event that we roll 2 5 more than once. Find the exact probability of E. Please pay attention. When they say exact probability of E, we're referring to binomial. Because the binomial will give you exact results. Okay, other approximation will give you only approximate results. An approximate result is not exact. Does that make sense? So I'm going to walk you through, using binomial, that will give you exact result. I'm also going to walk you through how do we use a normal approximation, and I'm going to walk you through how do we use a Poisson approximation. Now let's get started. Now, you look at the problem. Okay, we roll 2 dice 180 times. Okay, 2 dice at a time, 180 times. Okay, and the, event E, okay, the event that we roll 2 5 more than once. 2 5, like 5, this is a die, and I wrote them I wrote them 180 times, and I'm looking for 5 and 5 to show up more than 1. Now, if I want to do that, please pay attention. And I want to use binomial. Okay? If I want to use binomial, now I need you to see what I said here. Okay? Now, when I'm working with a die, just a single die, okay, the probability will be 1/6. Okay? But right now, okay, because I'm working with 2 dice, okay, I'm working with 2 dice, I'm tossing them, okay, the total combination will be 36. 6 raised to the power 2. Okay, we're going to have 36 possible number of combination, okay, and of course, each of the sample point in the sample space, they're going to have equal probability, and that will be 1/36. This is 1/36. You see 1/36 here, right? Okay, now if I want to use binomial formula, which is this guy now, okay, if I want to use binomial formula, please, I need you to pay attention. Okay, I need you to pay attention. If you don't understand, ask me a question. Okay, like I said, I actually want to use binomial. Okay, here, your n is 180. Okay, let me see. Yeah, 180 times, 180 rows. Okay, and x, okay, the number of times you roll 2 5s. The number of times, okay, number of times, okay, we roll, okay, 2 5s. The numbers of times we roll 2 5s. Now, the probability, and let me tell you this, is either we roll 2 5s or not. When I roll 2 5s, that will occur 1/36. If I do not roll 2 5, that will be the rest. That will be 35/36. In that situation, if P is 1/36, then Q, which is 1 minus P, will be 35/36. Does that make sense? Now, I know what to plug in here. Now, what is now my x? X the number of times, and they said no more than once. No more than once. No more than once. My S will be 0 and 1. No more than once means it could be less than 1. When it is less than 1, it's 0. S can be 0. Situation where S equal to 0, it means I do not have 2 5s. It's either it doesn't occur, and when it occurs, it shouldn't go beyond what? 1 time. Then my S will be 0 and 1. If I want to start now, what I'm actually going to do, okay, if I want to start, what I'm going to do, okay, I'm actually going to consider 180 combination 0, and that's what you see here. 180 combination 0, okay, I needed to pay attention to that. Then P, so the first one is going to be, so I want to find the probability of S less or equal to 1. The probability of S less or equal to 1 will be probability of 0 equal probability of 1. Now, the probability of 0 equal probability of 1, okay? Now, I needed to pay attention now. I want to find the probability of S equal to 0, okay? Which is going to be 180 combination 0, okay? P, 1 over 36 raised to power 0, 35 over 36 raised to power 180 minus 0. Now here, I'm actually going to have 180 combination 0. Anything raised to power 0 is 1, okay? Then 35 over 36 raised to power 180, okay? And that was why you're seeing this guy here. Now the second one, I'm also going to do the 1 for 1. S equal to 1. So 180 combination 1, 1 over 36 combination 1, 35 over 36 raised to power 180 minus 1. Okay, that was why, take a look at that. 180 combination 1, can you see that? 1 over 36, and 180 minus 1 is that. Now, finally, when I use my calculator or use your computer, this is what I'm going to get. But let me tell you this, without making use of computer, okay, maybe some years back, this would be very difficult to achieve. This will be very, very difficult to achieve. Now, the exact answer is 0.0386. Now, if I don't want to go through this, and I want to use approximation, please pay attention. Okay, if I want to use approximation, now in using approximation, I want to use a normal approximation. Please pay attention. If I want to use a normal approximation, don't forget, we want to find for S equal to 0 and 1. Now, S equal to 0 and 1 will mean I actually want to find X between 0 and 1. And in that very situation, okay, because it has to include 0 and 1. In that very situation, and I want to use normal approximation to binomial, then I have to apply a continuity correction. Now you can see less or equal to, then I'm actually going to go back first. I'm going to go back to my table of continuity correction. Now take a look at number 1. Can you see number 1, less or equal to? Then I'm going to subtract 0.5 from the lower bound, and I add 0.5 to the upper bound, which means I'm going to subtract 0.5 from 0. I'm going to add 0.5 to this before I use normal approximation. So now, finally, what I'm actually going to be working with is now going to be the probability. If I do that, I'm now going to be working with the probability of a negative 0.5 less or equal to 1.5. This is what I'm actually, after applying continuity correction, and I needed to pay attention to that, okay? Now, can you see that? That is why we have this. Can you see that? Negative 0.5, 1.5. Initially, it was between 0 and 1. But between 0 and 1, because we want to use a normal approximation, we actually need to apply continuity correction. Now, after applying continuity correction, now, if you take a look at what I'm doing here, what am I doing here? Okay, I'm trying to say 5 is the mean, n multiplied by p. Then the standard deviation is that. Of course, you know how I got that. Okay, the mean is going to be n multiplied by p. So in this case, 180 multiplied by 1 over 36. Okay, and the moment you get that, then I'm also going to do, the standard deviation as well. And at the end of the day, I'm going to go to the table. I'm going to check for value. I finally got it 0.0495. But can we do something here? Let's compare. We got it 0.0495 using normal approximation. But what do we get with the exact binomial? Okay, what do we get with the exact binomial? Now with the exact binomial, is 0.0386. But if you take a look at the two, right, it's 0.0386, it's 0.04, they are very close. Approximation is going to make sense if the result is very close to the exact. Now, this is using the normal approximation. Now, I want to use Poisson approximation, and I need you to pay attention. Okay? I want to use Poisson approximation, and I need you to pay attention. Okay? I want to use Poisson approximation now. Okay, now let me tell you this. When in a binomial distribution, when n is large, okay, when n is large and p is approaching 0, what is p? The probability of success approaching 0, okay, np will approaches lambda. np will approaches lambda. In fact, we got a proof. We can prove that limit n tends to infinity, n combination s, p raised to power s, q raised to power n minus s will lead us into this. We have a proof where when I take the limit of a binomial, the limit of a binomial will lead us into Poisson distribution. Now, it means when the sample size is large, when the numbers of trials is large, and the probability of getting success is very, very small, okay, NP converges to lambda. And if NP converges to lambda, then I can use a Poisson distribution for binomial problem. Okay, now the condition under which we can use normal for binomial problem is when NP is greater than 5. And when n into 1 minus p also greater than 5. But the condition here is when n tends to infinity, p tends to 0, np tends to lambda, I can use Poisson. Now, if I want to use Poisson for the same problem, okay, I want to use Poisson approximation now to the same problem. Okay, I want to use Poisson approximation to the same problem. And I need you to pay attention. Now, this is a Poisson formula. In Poisson distribution, the probability of S, like I said, is exponential per lambda, lambda raised to power x over x factorial. Now, I have to know that my lambda is NP. Okay, lambda equal to NP, and the problem we are solving, what is N? What is N? N is 180, okay? 180 multiplied by 1 over 36. Can somebody give us that? What is 180 divided by 36? Can you use your calculator? 5? Thank you. That gives us 5, right? Now, lambda equal to 5, okay? Now, if lambda equal to 5, because for me to use Poisson, I have to know my lambda. In a Poisson distribution, the parameter is lambda. Okay, that's why you see x follow poi with parameter lambda. Now, I want to find the probability of s less or equal to 1, okay, now the probability of s equal to 0 plus probability of s equal to 1. So what I'm going to do, okay, exponential, raised to power, 5 raised to power 0 over 0 factorial plus exponential raised to power dash 5 raised to power 1 over 1 factorial. Okay, now that's exactly what you're seeing here. And that gives us that. Now, I want us to now compare the answers. When you use Poisson, that gives us a 0.0404. When you use normal approximation, it's 0.0496. The exact binomial give that. They are all very close. So can you see the way that is done now? Okay, now that is how that is done. Is there any question? Go ahead.
Can you clarify why, for example, why we didn't use the continuity correction?
Why for which sample one?
Sample 1?
Number 1?
Yes.
This one?
No, further back.
Is it normal approximation?
Yes.
Or this one? So why we didn't use what?
No. You gotta go back.
Oh, back. Okay.
Example 1. We used normal approximation, right?
Yeah,
But we didn't use continuity correction.
exactly. Now, I decided not to use, so what I will now advise, so without using continuity correction, the error is going to be huge.
So that is wrong.
Yeah.
Right.
So it's going to be huge. It's not as if it's wrong. It's not wrong, but the error will be huge. Now, when you now apply continuity correction, you will have your error controlled. Does that make sense? Okay, so, but if you want to use normal approximation, always use continuity correction. But you now know the research I wanted to do now. When you use continuity correction, okay, compare your answer with this. If you want to know the one that is right, you know what you're going to do? You want to know the one that is right? Whether without continuity correction and with continuity correction, then use binomial. The binomial will give you the exact result. Then compare which of the two values is very close to the exact result given by binomial. Does that make sense? Okay. Now, I think I just showed you all of that. Now, lastly today, I think I've talked about linear combination before, and I want to reverse linear combination of random variable. Okay? If I have x1, x2 up to xn, they are independent, random variable, and each of them having normal distribution, then their linear combination is also a random variable will also follow normal. Take a look at this. If y is a linear combination of x1, x2 up to xn, and each of them, x1, x2 up to xn, follow a normal distribution, they have their mean, they have their variances. If I want to find the mean of y, there is also going to be linear combination of the means. If I want to find the variance of y, also going to be the linear combination of the variances. Why is it that I do not have a covariance here? Because we mentioned that x1, x2 up to xn are independent. Okay? And finally, if I want to write it in short form, if you take a look at this guy here, if I want to write this guy in short form, I'm going to write this. Summation AIXI, follow normal distribution with the mean. So the mean is good. I can also write this one in short form. Writing this guy in short form is this. And writing this guy in short form is what you have inside the square root. So what I'm trying to tell the world is that if x1 followed normal with the mean of 1, with the mean of mu1, the variance of sigma 1 squared, S2 followed normal distribution with the mean of mu2, the variance of sigma 2 squared, and so on like that, then I can find the mean and the variance of the linear combination. Okay, so I can find the mean of y, the variance of y. Then I'm also going to say, automatically, let me tell you, automatically, okay, if the variable that made up the linear combination, if each of them follow normal distribution, then their linear combination will also follow normal distribution. And that's exactly what we mean. Now, what are we gonna do next? Okay, we're gonna do exponential, gamma, chi-squared, and chi-square distribution. But let me tell you this. I want to appeal to every one of you, and I need you to listen. I want to use my next 5 minutes to talk about this, and I need you to listen. Are you ready? Are you all ready to listen? Okay, now listen. On Wednesday, I'm actually going to walk you through the practice questions for the exam, and I need every one of you to be around. Let me tell you this. Politicians will say election has consequences, right? Now, to students, exam also has consequences. Because you know why? You've been turning in, maybe you've been having good results for assignment. In assignment, you have the whole 7 days to complete assignment, and you can even consult somebody that may help you out in the assignment, but you know what, in the test, you're going to be by yourself. And that is the reason why I will need you to come to my class on Wednesday. Wednesday, I'm actually going to give you some, if I give you a question, okay, what am I expecting in terms of your response? Then I'm going to tell you some other information, what you need to bring to the exam hall, okay? Because you're going to be by yourself on the day of the exam, because there's not going to be any form of communication that will be allowed. You cannot seek assistance from your friend. You cannot even provide assistance. You're going to be on your own. And that is the reason why I will advise that you are present on Wednesday. Because on Wednesday, I'm going to walk you through, okay, this part, if I give you a question like this is what I'm expecting. Okay, don't waste your time. You're only going to have like 50 minutes for the exam. And how are you going to make use of, how you're going to plan wisely and turn out good results? Because what is going to make me happy, what is going to make me happy is when the least score in this class is 99%. That's what's going to make me happy. Or everybody can even score 100. I will be expecting you on Wednesday. That's all what I got for you today. Make sure you stay safe and have a lovely day. Bye for now, everyone. How are you? Yeah.
I won't be there Wednesday because there's a religious holiday. So, will you be recording all
Yeah, because I think I've defined a miss now, because the one I've been recording before doesn't come out good. So.